In this two-parter, we'll explore two descriptions of a probability model, its expected value and variance. Thus far, in studying random variables, we focused on building an appropriate probability model that summarizes the possible outcomes of a variable and their relative plausibility. But that's just the first step. Once we have a model in place, we should ask some follow-up questions. Mainly, what are the features of this model? Consider the following example. Suppose that your friend can take different routes to school, and let x and y be the commute times in minutes associated with two of these routes. Since commute times can vary from day to day, x and y are random variables. The probability density functions, or PDFs, describing these variables are plotted here. Now take some time to pause your video, examine the PDFs, and ask yourself, which route would you pick? Though these two PDFs have the same exact shape, there's one important difference. The typical value of x is lower than that of y. Specifically, commute times tend to be around only 20 minutes for the first route, but 25 minutes for the second. Thus, the first route is better. Let's compare this first route with commute times x to a third route with commute times z. Again, pause your video, examine the PDFs, and ask yourself, which route would you pick? In this case, the typical values of x and z are the same. Both routes tend to take 20 minutes. But there's still a key difference between the two. Notice that the PDF of z is much more spread out, hence there's more variability in commute times from day to day. Specifically, whereas the commute times x for the first route are consistently between 15 and 25 minutes, the commute times z for the second route tend to vary between a much wider window, roughly 8 to 32 minutes. Now, which route you think is better somewhat depends upon your risk tolerance. Though your friend might occasionally get lucky with the second route and get to school in as little as 10 minutes, they might also get unlucky and take more than 30 minutes to get to school. In comparison, the first route is less risky or more dependable. These examples illustrate two important features of a random variable, hence two important follow-up questions. What is a typical value of x, and how much variability is there in x from observation to observation? In this video, the first of two parts will focus on the first question. To this end, there are three common approaches to measuring the typical value of a random variable: mean, median, and mode. First, the mean or expected value of a random variable is the weighted average of all possible outcomes of x. Second, the median marks the middle value of x. There's a 0.5 probability that an outcome of x falls below the median, and a 0.5 probability that it falls above the median. With this in mind, the median is also referred to as the 50th percentile. Finally, the mode marks the most plausible value of x. Some examples can help us distinguish between these concepts. First, consider a perfectly symmetrical unimodal random variable that's centered at 0. In this case, the mean, median, and mode are all equal to 0, hence all equal to each other. Specifically, 0 is the average or mean outcome. Half of the outcomes fall above, and half fall below 0, hence 0 is the median. And 0 is the most plausible outcome, hence mode. That is, the PDF is highest when x equals 0. But it's not always the case that our three measures of what's typical agree. For example, consider a right-skewed PDF. In this case, the PDF is highest when x equals 2. Thus, x has a mode of 0.2. Unlike the mode, we aren't able to calculate the exact median and mean from the visualization alone. However, some calculations, which we won't do here, prove that there's a 50% chance that x falls above or below 0.34. That is, the area below the PDF or under the PDF is cut in half at the median. Finally, the mean or expected value of x is even higher at 0.4. In general, notice that when a random variable is right skewed, the additional outcomes in the right tail pull the median higher than the mode. And they pull the mean even higher. Essentially, because the mean is taking into account the average outcome of all possible values of x, including those that are way up here. For the remainder of this video, let's focus on the expected value or mean of a random variable. Consider an example. Suppose that a soda factory sells 12-ounce cans of soda. Let x be the discrete error in the actual amount of soda in a can in ounces. Further, suppose that x has probability mass function, or PMF P of x, as summarized in the table here. Notice from the table that there's a 50% chance that x equals -1. That is, that there is 1 fewer ounce of soda than advertised. There's a 30% chance that there's 0 error, hence exactly 12 ounces in the can. Finally, there's a 10% chance that the can is overfilled by 1 ounce, and a 10% chance that it's overfilled by 2 ounces. So taking this into account, how much error can we expect there to be in a can of soda? Or what's the average error? A first attempt at calculating the average value of x might be to simply value up the possible outcomes of x. That is, we can add up -1, 0, 1, and 2 and divide by 4. Equivalently, we can give an equal weight of 0.25 to each of these possible outcomes. The result of this calculation would be an average error of 0.5 ounces, a positive amount. But this would be incorrect. Putting equal weight on each possible outcome in this way assumes that these outcomes of x are equally likely. For example, it ignores the fact that the machine is much more likely to underpour, that is, for x to be -1, than it is to overpour, that is, for x to be a positive value, like 1 or 2. Instead, to calculate the expected value of x, we can calculate the weighted average. Specifically, we weight each possible outcome of x by its corresponding probability, and then add these up. So x equals -1 with probability 0.5, or x equals 0 with probability 0.3, or x equals 1 with probability 0.1, or x equals 2 with probability 0.1. By this calculation, notice that on average, the machine underpours by 0.2 ounces. In mathematical notation, E of x represents the expected value of x. Next, let's tweak this example. Suppose that the company loses some money for any error that they make, and that the amount of money they lose depends upon how big the error is. Specifically, let y equal x squared be the money lost in cents. For example, if a can is overfilled by x equals 2 ounces, then the company loses y equals 2 squared, or 4 cents. Now, note 2 things. First, y equals x squared, thus, y is a function of x. Thus, just as the error x can vary from can to can, the money lost, y, can also vary from can to can. That is, y is a random variable. Therefore, just as we can ask about the expected error x in a can of soda, we can ask about the expected amount of money lost, y. There are 2 approaches that we can take here. The first one follows 2 steps. First, build the probability model of y, and then calculate the expected value. The PMF of this model is shown here. Let's break this down. First, notice that since x can be -1, 0, 1, or 2, then y equals x squared can be 0, 1, or 4. Next, y equals 0 when x equals 0, which happens with probability 0.3. Similarly, y is 4 when x is 2, which happens with probability 0.1. Finally, y is 1 when x is either -1 or 1, which happens with a combined probability of 0.6. With the PMF in place, we can calculate the expected value of y, weighting y equals 0 with probability 0.3, y equals 1 with probability 0.6, and y equals 4 with probability 0.1. By this calculation, the expected money lost on a can of soda is 1 cent. Now, this method of calculating the expected value of y works, but there's also a more efficient approach. Since y is a function of x, we can calculate the expected value of y directly from the PMF of x. That is, there's no need for us to take the additional step of building the PMF of y. To this end, we take each possible outcome of x, square it, and weight it by its corresponding probability. Specifically, x equals -1, thus y equals -1 squared with probability 0.5. X equals 0, thus y equals 0 squared with probability 0.3, and so on. The result of this calculation is the same as when using the first method. On average, the company loses 1 cent on a can of soda. In conclusion, to calculate the expected value of a discrete random variable x, we sum up the possible outcomes of x weighted by their corresponding probabilities. Similarly, to calculate the expected value of a function g of x, we sum up g of x at each possible outcome of x, weighted by the corresponding probabilities of x. Now, we didn't see an example of calculating an expected value for a continuous random variable, but the idea is similar, except we replace the sums with integrals. Mainly, we're still averaging over all possible outcomes of x, weighted by their corresponding PDFs, or densities, f of x. Finally, to connect this theory with practice, recall the commute times x for your friend's route to school. According to the underlying probability model of x, we expect that route to take 20 minutes. To consider how this plays out in practice, suppose we collect data on your friend's commute time on 1,000 different days. Just as the distribution of these sample outcomes approximates the underlying probability model, that is, the histogram looks very much like the PDF, the observed mean commute times on these days, at 20.07 minutes, approximates the underlying expected value, 20 minutes. Thus, we can think of the expected value of random variable x as the long-run sample mean of the observed outcomes of x. That is the average value if we observe x over and over and over and over.